Hello physicists, welcome to our April 23rd edition of Physics. Today's video should be a little bit of a short one because we took a quiz in class today. I should have communicated with you about this if you were one of the people who contacted me about missing today, or if you're taking this remotely. Otherwise, be prepared to take the quiz after class on Monday. Okay, now on Monday we went through most of the big ideas of Unit 1 and we didn't quite have enough time for uniform circular motion. So that's where we're going to start today, and we'll do circular motion, then dip our toe into the sorts of ideas that we revamped this with in Unit 3 and apply uniform circular motion directly to gravity, because that's really the Unit 3 topic that is most relevant to this concept. So what was the idea of uniform circular motion? Well, the idea was that, let's say you are moving around in a circle. Well, the thing that's allowing you to move in a circle, even if you're going at a constant speed, so let's say your instantaneous velocity when you're at this point on the circle is going to be pointed tangentially to the radius of the circumference of the circle. The acceleration that keeps you moving is going to be perpendicular to the velocity, and that acceleration, that centripetal acceleration, is pointing towards the center of the circle, and it's causing this velocity to change direction. Not to change speed, but just to change direction. Now, if we have a circle of radius r, we derived that the centripetal acceleration, the size of it, was related to the speed at which you're going around the circle and the radius of the circle itself. Of course, those things are not totally independent. I mean, these are independent, but let's say that I wanted to think about the time to go around the circle. Well, the time is just going to be the total distance around the circle the speed is going to be the total distance around the circle, but divided by the time it takes to go around the circle. So you notice that if you wanted to put your v in terms of for instance the period, that would depend on r, and sticking this in there, you would have to worry about having the r in the numerator and the r in the denominator. Okay, but let's not worry about that right now. It says a particle moves at a constant speed in a circular path. The instantaneous velocity and instantaneous acceleration vectors are both tangent to the circle path. No, because they're whoops, I'm pressing my erase button on my cursor. No, the v is tangent, the a is not. Both perpendicular to the circular path. No, a is perpendicular, v is not. Perpendicular to each other. Yes, they are. Opposite to each other. No, they're not. They are opposite would be if AC was pointing in the other direction. And none of the above. No, this one is okay. Okay, so I'm going through questions that are on your review packet. By the end of this review, I'm going to have basically done a lot of the review packet. The review packet is fairly long, but just realize that the way I'm going to be grading it is I am going to just glance at it as you hand it in to me during your exam period, and I'm hoping to basically get it graded during that exam period, because I just want to say, okay, did they do it? Did they not? And I want to give you points. So it's not the purpose of this review packet is not to give you extra work. It's to help you prepare for the exam, and I think it should be helpful. So here's another question. Now, it says two objects are traveling around different circular orbits with constant speed. They both have the same acceleration. Okay, so let's call them object A and object B. So acceleration of object A equals the acceleration of object B. They both have the same acceleration, but object A is traveling twice as fast as object B. Okay, so VA equals 2 times VB. The orbit radius for object A is what times the orbit radius for object B? Well, let's expand out this acceleration equals acceleration because I know a little bit about the connection between the acceleration and the speed from this angular acceleration formula. So VA squared over RA equals VB squared over RB. Okay, so that's just me saying that these are both objects in uniform circular motion. They're both going at some speed and some radius r. Now, I'm going to use my other piece of knowledge and put in my 2VB. So 2VB squared equals over RA. And then I have VB squared over RB. And now I can expand this out and divide both sides by VB squared. So that would give me 4 over RA equals 1 over RB. And now I can just cross multiply, and that gives me that RB equals 4RB equals RA. So the orbit radius for object A is 4 times the orbit radius for object B. So as you know, I like this type of question, and I put them on tests at any opportunity I get. I think I may be the only person around who likes these, though. Okay, so next, in Unit 2, we introduced the idea of centripetal force. All this was if you have a centripetal acceleration, if you use F equals ma, if the centripetal acceleration is the net force that's acting on it, then that net force equals the mass times the acceleration. And the idea that applied most directly to was Newton's law of gravitation. But before we did that in Unit 3, we talked a lot about angular coordinates. And so just to dip our toe in there, let's do 2 problems with angular coordinates and realize how these problems are very similar to what we did last class in our Unit 1 review. So, okay, here we go. It says the coordinate of an object is given as a function of time by theta equals 7t minus 3t squared, where theta is in radians and t is in seconds. So this would be seconds, this would be seconds squared. Now, going back to our analysis from our video on Wednesday, this 7 would have to have units of radians per second, and this 3 would have to have units of radians per second squared, because if on the left we have units of radians, on the right everything that we're adding together also has to have units of radians. Now, something that's a little bit confusing is that let's say you wanted to go to linear velocity, right? The way you get linear velocity is by taking your angular velocity and multiplying it by meters. So this would be, you know, in the case here, let me do it on a different page so we don't confuse it. V equals, let's in fact do it in a simpler example. Let's just do S, the distance in meters, equals theta times r. Now this is a little confusing because theta is in radians, r is in meters. So if you look over here, you want to say, okay, distance must be in radian meters. But there's something funny about radians because often we treat them just as not a unit. And the reason for that is they're the ratio of the arc length on the circle to the radius of the circle. The arc length to the radius gives you the radians. So because this is a ratio, it actually doesn't have units. And this is just meters. So, like in this case, if I wanted to translate that theta into a distance in meters, I would just have to use, my distance in meters equals theta times the r of the circle, and that would give me how far my object is moving. Okay, so a little side note here. Now, it asks me for the average velocity. Well, you know how to find the instantaneous velocity from the instantaneous position. This is an angular position. You know that to find the instantaneous velocity, you just take the derivative. So 7 minus 6t. Now, interestingly, you actually do not need to do that in this case, because to find your average speed, what you need to do is to find your total displacement over your total time. What does that mean? That means you want to find what is my theta at time equals 2 seconds, minus my theta at time equals 0 seconds, divided by 2 seconds minus 0 seconds. Okay, so you get to put in 2 into this equation, get your theta at time equals 2, put 0 into this equation, that'll just give you 0. And you can calculate this out. Okay, so I'm going to let you do that, but I just want to draw your attention to the fact that I know you want to take the derivative when you see this, and it's something you know how to take the derivative of. At least I feel that way. But in this particular case, they're asking for the average velocity, not the instantaneous. So when you do your problem, you're going to have to distinguish between what you're being asked. This is your instantaneous angular velocity, and then this one is your average average angular velocity. Okay, so be careful. Now, that's sort of an old idea in a new language, but I want to sort of stress what is new about this idea. The new part, and I know I've said this before, but I am not afraid of being redundant. The new part is that if you have something like a watch handle, and this is swinging around and around and around, the part that's on the inside of the watch is going more slowly than the part that's on the outside. And that's because it's moving over less distance in the same amount of time. However, you don't want to necessarily talk about this in those terms because you're thinking about this watch hand as a single object, and it's more convenient to talk about it in angular terms. So just to get us to think about the parts of a watch, the second hand goes around once every minute. The minute hand goes around once every hour. The hour hand goes around once every 12 hours. So let's try to think about this. It says the angular speed of the minute hand of a watch. So that's our omega. A minute hand of a watch, how often does it go around? Well, it's telling us 1, 2, 3, 4, 5, 6, 7, all the way up to 60. So it goes around one revolution in 1 hour. Okay, and then if you want to convert that to the correct units, you would do 2 pi radians is 1 revolution, and then 1 hour is 60 minutes, and then 60 minutes, 1 minute is 60 seconds. Okay, so there your hours cancel out, your revs cancel out, your minutes cancel out, and you end up with radians per second. And if I cancel out a 2 there, I can make this into a 30. 30 times 60 is 1800, so my omega would be pi over 1800 radians per second. Okay. Now, our last thing that I want to cover in this video is the idea of gravity as a centripetal force. So let's say that you have an object right here. So this could be the Earth or the Sun or whatever is being revolved around. Now, on our test last week, I had some of you who got this wrong on the true-false. The question I asked was, is it true that the reason why a satellite is able to go in its orbit, is it true that that's because if you go out farther, the pull of gravity gets so weak that it basically doesn't pull on you? No, that's false. In fact, you need that force of gravity because that is the thing providing the centripetal force. Okay? The idea here is just that you're going fast enough. So, just to say it a different way, if your object is just staying still out there in space and you let it go, it will accelerate and accelerate and accelerate and get faster and faster and faster until it hits the Earth. On the other hand, if you give it some angular or some speed that it's going around that circle, it can go fast enough so that as it falls, it continually misses the Earth. So it is being accelerated. Gravity is still pulling it towards the center of the Earth, but it's falling and falling and falling and falling and falling. Okay, so the idea here is that that force of gravity is the centripetal force. It is that mass times centripetal acceleration. And this gives you a very close relationship between that R and the V and the mass of your object that you're orbiting. It turns out that the mass of the satellite doesn't come into play. Why is that? Well, let's see quickly. If we have our centripetal force equals gravitational force, then I can go and say mv squared over r equals g, that's that 6.67 times 10 to the minus 11 newtons times meters squared over kilograms squared. M for the mass of the satellite, big M for the mass of the thing being orbited, like the Earth in the case of a communications satellite, over r squared. And that r is from the center of mass of the satellite to the center of mass of the Earth. So basically the center of the Earth. Okay, now look, there's a mass of the satellite on both sides. That cancels. Multiply both sides by r, take the square root, and I get v equals gm over r. Okay, so there's in a circular orbit, there's a very close relationship between the mass of the thing being orbited, that would be like the mass of the Earth, the distance at which you're orbiting, and the speed that the satellite is going at. So let's see this in a specific example. Now, remember, I told you the exam is going to be due on the review is going to be due on the day of the exam, and it's super helpful to do this because I'm not exaggerating here. The questions on your review, the short answer questions on your review, are exactly the same questions that are going to be on your exam. All I'm going to do is change the numbers. So if you understand the questions on your review, you are going to knock the exam out of the park. So, for instance, in this question, I say a 40-kilogram satellite maintains a circular orbit around the Earth, 10,000 kilometers above the Earth's surface. So those are the numbers that I get to change, and then everything else in the question is going to be the same on your final exam. Okay, so then A asks, what gravitational force pulls the satellite toward the Earth? Okay, let's see. Well, if I just want to find the force, I have an easy equation for that. Let me draw a little picture for myself. I've got the radius of the Earth, and then it says that it's in orbit 10,000 kilometers above that. So there's my circular orbit where my satellite is now going. Let me just draw it a little better. It's going around here. So this is my distance above the Earth. So the R that I would use is going to be 10,000 kilometers. So if I want to put that in meters, it would be 10,000 meters. That's this distance, plus I have to go to the center of mass of the Earth, so that would be plus an extra 6,378 times 10 to the third meters. Okay, we're given the mass of the Earth, so that would be my big M, 5.974 times 10 to the 24th kilograms. So I gave you that one in good units. M of the satellite is 40 kilograms. So I gave you that in good units. Okay, so what gravitational force pulls the satellite towards the Earth? Well, at this point you can simply put all of your numbers into this. And let me just put it this way. G on Earth is around 10 newtons per kilogram. So if this satellite were right here, right on the surface of the Earth, you'd get about 400 newtons. So you should get some number smaller than 400 newtons and bigger than 0. Okay? So that's a good rule of thumb. B asks, what is the speed of the satellite? Well, on our previous slide, I showed you how to get that. It would be square root of gm over r. Now, there's another way that you could get that, and that's by doing c. Now, it asks, how long does it take the satellite to go around the Earth once? So if you put in g and m and r in good units, you're going to get a v that's in meters per second. And if you wanted to find the time it takes, well, that would just be the total distance, 2 pi r, so the radius of this big circle, divided by v. That'd be one way to do it. Another way to do it would be to use Kepler's law of periods. In that case, you could find the period, and you could then put in the mass of the Earth. You could put in the r, this big R, and find out the total time in seconds. And of course, if you found that first, then from this you could find out what your v is. So you could do this. I am only going to give you the Newton's law of gravitation and Kepler's law of periods. I'm not giving you this nice equation, but you can always derive that. Or you can do this the other way and find your period first and then find your velocity. Okay, so that's all I'm going to do today because you have a quiz to take. On Monday we're going to be doing, and Monday and Wednesday of next week we're going to be reviewing Unit 2 and Unit 3. Friday of next week we don't have class because they're giving you time to prepare for your exam. Your exam is next week, Tuesday. And as a reminder, remember I am giving extra credit for doing course evaluations. If 90% of everyone in the course does a course evaluation, I'll give you 5% extra credit on the exam. So please do that, and please try to think of helpful hints to improve this course. If you can think of things that would be helpful to you, I do take them seriously, and that might even translate into making this course or your second semester of physics more reasonable if you have me in the fall. Okay, so thanks for watching.